Okay, thank you, Josie. So, hello everyone. So I'm Seppe Terryn and I'm a postdoc researcher at the Vrije Universiteit Brussels. And I will present our work on self-healing robots and how the integration of self-healing polymers in robots can actually also impact the embodied intelligence or physical intelligence. But before I will go to the motivation why we actually need these self-healing robots, I want to thank the organizers of this Embodied Intelligence Conference for giving me the opportunity to present our work. So first of all, soft robots, yeah, they have a lot of advantages, but there are also disadvantages. And the main disadvantage is that these soft robots being soft, the softness comes with a price because these systems can be damaged quite easily, and there are a lot of different damaging conditions which lead to early failure. So they can be damaged by sharp objects, so they can be cut, punctured. They're also prone to fatigue, to tendon cut. If you overload them, they also tend to break or burst if they're a pneumatic system. And if you have actually multiple materials inside of a soft robot, then delamination occurs also. So it's the interfacial debonding of multi-material interfaces. And all these damages, they actually lead to these robotic systems which have a limited lifetime. And this, of course, leads to non-economic solutions. And therefore, actually, in a lot of applications, this limited lifetime is preventing the large adoption of these soft robotic systems in industrial and in commercial applications. And of course, sustainability is also very important, as shown by these initiatives of the EU, for example. So in the future, we need to make robots which are sustainable, which have a long lifetime. And how we tackle this problem is actually we make them out of self-healing materials. And these are reversible polymers. So they consist out of a reversible chemistry. In our case, it's the Diels-Alder chemistry. And therefore, they can heal from small damages, but also large damages like the cuts you can see there in the videos. And for these particular prototypes, the healing works by applying heat. So we heat these hands or these muscles to 80 degrees for only 40 minutes. And then these damages, they are completely healed. So these systems are, again, as good as new. So this means that the healing can also take place for multiple times, and therefore the lifetime of these components can be increased a lot in future applications. Now, how does the healing work? Well, we have a polymer network structure, and in this network structure, the connection points are Diels-Alder bonds, which are reversible. Now, if you cut, then locally you break these Diels-Alder bonds. And if you then want to heal, then we need to increase the temperature. Now, if we increase the temperature, then throughout the network, we will break additional bonds. And these Diels-Alder bonds, and this gives more mobility and also more reactivity. Now, because you have more mobility on the molecular level, you can start sealing gaps on the molecular and microscopic level. So you first seal the gaps, and when everything is sealed, we can actually start decreasing the temperature again. And because we decrease the temperature, being reversible, these bonds, they will reform in the network throughout the material, but also across these fracture surfaces, and then everything is healed and the initial properties are completely recovered. So the healing can take place for multiple times. So this is what you can also see if we zoom in. This is a bit fast forward the movie, but you can see that if we increase the temperature, that our mobility is increased and we can start sealing these damages. Now, if we look at physical intelligence or embodied intelligence in nature, but also in robotics, we can actually increase it by having multiple materials inside of a single design. So if you look at a human hand, it is composed out of really a lot of different materials with a lot of different stiffnesses, and therefore we have really a high embodied intelligence. Now, if you look at soft robots, there are already some examples on multi-material soft robots, but there are still a lot of challenges. And one main challenge is that the interface of these different materials causes usually some problems because of this interfacial debonding. And this leads again to systems which are not robust and which have a limited lifetime. Now, the materials that we make, they can also provide a solution for this. So being polymer scientists, we can actually change the composition of the material. So we can change parameters in our polymer networks and then tune the properties, and this can be the mechanical properties. So we can actually make very strong, very hard materials, and we can also make very soft, hyper-elastic materials. Now, but in all of these materials, we have the same reversible crosslinks, which are the Diels-Alder polymers, which are the Diels-Alder reactions, sorry, and therefore we can actually put these two parts together, so two parts which have completely different mechanical properties. We apply a heat-cool cycle, and while everything stays solid, we can actually bind these two surfaces together. And the result is that we have a very strong multi-material interface, which we can use in soft robots. And this is what we did. So the robotic systems that you can see there are composed of multiple materials. But the interface is very strong, very robust, so the part will not break there. And everything is still healable, so you can actually also cut through these actuators or fingers, put it back together, and if you apply heat, it's 90 degrees in this case, then everything is healed again and as good as new. Now you can put materials with different mechanical properties together, but you can also reversibly separate them again. So you can actually, parts at the interface you can cut, you can then swap one of the materials and put it back together, apply heat and cool down, and then it will be bound again. So this opens, I think, also these new materials open a lot of possibilities for modular and reconfigurable soft robots in the future. And we showed also that we can do a transformation from 2D structures to 3D structures. So you can actually cut a certain shape out of a sheet and then fold it together, also a bit like origami. And then you can seal or connect these sides by doing, again, a heat-cool cycle. And by so you can actually try and lock a certain configuration inside of your part or your actuator. So again, I think this is for future reconfigurable robots very, very interesting. Now we've also been developing conductive self-healing materials. So we apply fillers in our material to make them electrical conductive. And then we developed some strain sensors and capacitive sensors, which have a good response. And you can also cut them completely in half, put them back together and apply a heat-cool cycle. And then they will be, they recover their mechanical properties, but also their electrical and sensory performance. So this is, of course, interesting because you increase also the lifetime of these components, which are also vulnerable as they are composed of flexible materials. But what is also very interesting is that you can have multifunctional sensors because they can be used for deformation and force or touch tracking, but they can also be used for damage sensing and localization. Because if you cut a sensor, of course, you will also see it in the sensor response. And you can also use them for healing and recovery monitoring, because when you are healing, you're actually recovering your sensor properties. So that means that you can also track the healing and see if it's carried out in the correct way. And I think this is very important for future physical and embodied intelligence, that we look at multifunctionality on the component level, but also on the material level. Now, the next example that I want to show is that we make also self-healing heaters, which are flexible. So they're also composed of a self-healing composites, which is electrical conductive. So we made this heater and we embedded it in a finger actuator. And you can cut the complete actuator and the heater in two, and you can put it back together. And then you have recontact. So we can apply a current to heat up the heater. However, you have also a higher resistance at the location of the damage. And I think this is very interesting, as you will have a self-targeting heating and healing in this case. So if you apply a current, then the location that will be heated and healed is the location of the damage. So this is another example, I think, of an embodied intelligence. Now we are trying to increase the lifetime of our components by using self-healing, but we also target sustainability on different aspects. So we do also recycling. So the materials that we use, they are completely recyclable, and this mechanically, but also chemically. And we are using now renewable resources and making them more biodegradable, also in view of making them more sustainable. So this was the presentation, and I hope we can have an interesting discussion in a panel discussion.
Thank you very much, Seppe. I think it's very nice to actually touch on recycling, circular economy, and actually bring us into robotics. So thank you very much for that. One question I just quickly had is, when I think of self-healing, often I think there's a loss or there's a compromise in the functionality, or perhaps the quality of the sensor response, or the material strength in the polymers. Do you think that that's true? Is it a compromise, or has polymer science really advanced such that we don't lose functionality or capability by introducing self-healing?
I think, to be honest, it's always it's still present that there is a trade-off between the other properties and the self-healing property. However, there are some tremendous advance in these self-healing polymers, which really show that they are mechanically stable and so on. But yeah, to go to commercial applications, I think we still have to see if we meet these very high requirements for certain products and applications.